Jnanam paramam dhyeyam. Knowledge is supreme.
Welcome to this lecture on advanced transition metal organometallic chemistry. We have been discussing transition metal cyclopentadienyl halide complexes. In the last lecture, we had seen how these halide complexes are important organometallic compounds, which can give rise to many other very useful reagents, and these are obtained by conversion of these transition metal cyclopentadienyl halide complexes to these particular reagents. To begin with, we saw that these compounds can be converted to simple aqua complexes just by abstraction of the halide using silver salts, and these aqua complexes are useful examples for that depicts two aspects of chemistry, which is the organometallic aspect by virtue of having transition metal cyclopentadienyl bond, as well as the coordination aspect by virtue of having the aqua transition metal bond. So, transition metal cyclopentadienyl halide complexes can be converted to the aqua complexes by simple abstraction method. Now, we have also seen how these transition metal cyclopentadienyl halide complexes can give rise to another useful reagent in the form of getting converted to transition metal cyclopentadienyl mixed halide hydride complexes, which is just called Schwartz reagent, and that is useful for converting olefins via hydrozirconation to various useful organic intermediates and products. We have also seen in the last class the versatility of Jordan's cation, which is nothing but a bicyclopentadienyl zirconium methyl THF cation, and this compound primarily is a versatile active catalyst for many kind of transformations like CH activations, CC coupling, as well as polymerization reactions. And we had taken up examples in which we could see that these Jordan's cation reacts with alkyne, olefin, carbon monoxide via coordination insertion pathway, as well as it reacts with alkanes via sigma metathesis pathway, generating the corresponding alkyl derivative along with formation of the methane. So, continuing further on this transition metal halide complexes, we are going to look at another interesting family of compound which are derived from these transition metal cyclopentadienyl halide complexes, and these are called transition metal cyclopentadienyl halide carbonyl complexes. Okay. And these are also important reagent in organic synthesis. So, mixed cyclopent CP metal carbonyl halide are important reagents in organometallic synthesis. And some of the examples of these compounds are molybdenum, tricarbonyl chloride or Cp iron chloride dicarbonyl or Cp nickel iodide, and the preparative method involves oxidative cleavage of the dimers using dihalogen compounds. So, these methods they are prepared by oxidative cleavage of dinuclear precursors by dihalogens. An example of this is shown over here. So, Cp Fe dicarbonyl dimer plus iodine giving 2 molecules of Cp Fe dicarbonyl iodide. So, this method is kind of a general method and involves the oxidative cleavage of dinuclear compound by reacting with dihalogens. Now, these Cp iron carbonyl halide complexes are important starting points for creating other kinds of complexes, and here is a nice demonstrations in which this mixed carbonyl halide complexes can be converted to another interesting compound which contain both Cp bound in eta 5 as well as eta 1 fashion. So, I will illustrate this with an example shown over here. So, Cp star iron dicarbonyl iodide when treated with AgBF4 in presence of cyclopentadienyl gives. First, the abstraction of this iodide happened, resulting in the formation of silver iodide along with this olefin bound complex to iron results, giving Cp star Fe the iron complex of this, and it is a cation because this halide had been abstracted. Now, in presence of a base, one of the protons get deprotonated. The base can be triethylamine, resulting in 83NH plus, which eliminates to give this Cp star Fe CO olefin compound. So, this is an interesting compound where we see that it contains eta 5 bound Cp as well as eta 1 bind cyclopentadienyl ring, and the binding of this the differential binding of this to cyclopentadienyl ring is easily picked up in proton NMR spectroscopy, where the fluxionality of these protons is greatly visible. So, what we see is that there are several types of new compounds or new subclasses that can be obtained from cyclopentadienyl transition metal halide complexes, and these being its aqua complexes, its mixed halide hydride complexes, its alkyl base cationic complexes which are Jordan reagent, and then its mixed halide carbonyl complexes. So, and all of these offers different perspective or different new chemistry, and that is why it overall this makes this transition metal cyclopentadienyl halide complexes so interesting. Now, we have covered most of the topic for this half sandwich class of compound, and we are going to now move on to another interesting class of compounds, and these are transition metal arene complexes. So, with this we make a transition from 5-membered ring cyclopentadienyl ring to the 6-membered arene complexes. So, from now on in this lecture we are going to be discussing on arene complexes, and to start off we are going to look at the simplest the most simplest of all, that is the benzene complexes of these transition metals. So, today we are going to be discussing C6H6 as ligands, and these are called arene complexes. Now, these like the cyclopentadienyl complexes, where C5H5 binds through the pi electron in a eta 5 fashion. Similarly, the transition metal forms eta 6 arene complexes. Metals form arene complexes, and now with respect to the main group, such main group transition metal arene complexes are considered to have weaker interactions, and they are not as common as that of the transition metals. So, this is an important observation, that main group elements metal arene interaction is weak, and hence they do not occur that often as compared to its transition metal complexes. Now, transition metal arene complexes, these binary bis arene metal complexes similar to that of the Metal-ocene are quite common, and they are particularly called as these bis arene metal complexes. So, these are binary arene complexes which are quite common, in which the arene binds in eta 6 fashion. The synthesis is commonly referred to as Fischer-Hafner synthesis. This is quite a general route for making these compounds, and the first synthesis was reported with chromium 3 Cl3 plus twice Al plus 6 arene, giving 6 arene in presence of AlCl3 and water giving 3 arene 2 chromium plus twice Al 3, this in presence of Na2 S2O4 and KOH gives this eta 6 arene whole 2 chromium. Now, this is quite a versatile synthesis, and the scope is for vanadium, chromium, iron, cobalt, nickel, then molybdenum, technetium, ruthenium, rhodium, tungsten, rhenium, osmium, iridium. So, it seems that this is quite a interesting bit of reaction, because it is quite general for so many different metals, but the only limitations that it offers is that arene must be inert towards AlCl3. The only limitation is arene must be inert to AlCl3, because sometimes this alkylated arenes are isomerized by AlCl3 and so on and so forth. So, these this does have a limitation that these arenes should not be attacked by AlCl3. Otherwise, if that is not the case, then this Fischer-Hafner synthesis is quite an useful synthesis for preparing this bis-arene transition metal complexes. So, we are going to dwell upon some other interesting reactions which are useful for preparing these bis-arene complexes. And the next one is by cyclotrimerization of arene. The next reaction is so to illustrate this, let us take a look at this example. C6 H5 whole 3 chromium THF whole 3 plus CH3 CH3 in presence of THF 20 degree centigrade, water, oxygen, giving this bis-arene complex of hexamethyl benzene. This is a interesting reaction which sees that the metal sort of trimerizes alkyne this methyl C111C methyl to gives this hexamethylene benzene, and then subsequently forming a sandwich complex of that. This is a very elegant way of making this bis arene complex in which these two of the hexamethyl rings are bound in eta 6 fashion parallel to each other, similar to what has one seen in Metal-arene type of complexes. So, the next reactions is also a very interesting one and that involves reductive complexation. The reductive complexation involves the reaction of metal halides with radical anions, and so this reaction is useful for ligands which can be easily led to the formation of its radical anions. So, this reaction sort of proceeds for metal halides plus radical anions, and hence ligands that readily form radical anions are good for this method of synthesis, are good for this method. Now, example of such ligand is this naphthalene. And in its the naphthalene forms readily radical anion. For example, with lithium it forms LiC10H8. This is the radical anion, and then the reaction MClN THF 6 minus N plus N LiC10H8 giving eta 6 bound C10H8 whole to M plus N LiCl. Now, this is quite a common method for chromium, molybdenum, and N equals 3, and for vanadium for N equals 4. So, this reductive coupling is a unique reaction so far that we have been seeing, that involves converting the ligands to their radical anions and then treatment of the radical anions to the metal halides, and nice demonstration of this have been used in case of various metals like chromium, molybdenum, vanadium that produces this anion. We are going to look at another such example that involves this radical anion, and this one is with biphenyl or C12H10 ring. So, C12H10 is biphenyl and its radical anion is potassium C12H10 radical anion. So, the reaction is TiCl4 THF whole twice plus 5 KC12H10 at very low temperature minus 78 degrees centigrade, giving K Ti C12H10 whole 2 plus 3C12H10 plus 4KCl minus Ki and presence of iodine gives this pH. It has 6 bound C5H5 whole 2 titanium. Now, here we see that two of the two biphenyl ring, one of the biphenyl ring is bound in a eta 6 fashion to titanium. Now, another example of this reaction is reductive coupling is shown over here, that involves this zirconium tetrachloride THF whole 2 in presence of KC10H8 and cryptand 3,2,2,2 cryptand in DME, and the temperature is from minus 60 degree C to 0 degree C. Then one gets 2 potassium 2,2,2 cryptand plus this very interesting compound bound to zirconium this to minus. So, okay. So, here this is an interesting example of this reductive coupling, where it reacts with naphthalene, but with only the naphthalene only with the two of the olefinic bonds of the naphthalene. As a result, the naphthalene ring is sort of no longer planar and is found bound to zirconium in a metallic dianionic form. So, with that I conclude today's discussion on these transition metal cyclopentadienyl halide complexes as well as the corresponding bis-arene complexes, and to summarize, we had looked into these various methods of preparation of these transition metal bis-arene complexes, and some of them involved using the reaction of halides, metal halide precursors with arenes in presence of reducing agents like aluminum. This was Fischer-Hafner synthesis. One has to this is quite a general reaction, but one has to be careful that the arene does not react with AlCl3. The other method involved was this the reaction of metal halides with the ligands which can form radical anion, and these are called reductive coupling. We had seen some useful interesting examples which are successfully used in producing for these transition metal arene complexes using this method. So, with this I would like to draw a conclusion on today's lecture, in which we have looked into bis-arene as well as transition metal cyclopentadienyl halide complexes. In particular, in that front we had looked into the mixed transition metal cyclopentadienyl halide carbonyl complexes and how they are also used in making interesting compounds in which we had one eta 5 bound CP and another eta 1 bound CP rings. So, we are going to continue more on this discussion on transition metal bis-arene complexes in the next lecture. Until then, I will goodbye, and I thank you for patiently listening to this lecture today.